The F-28 was designed to be independent of ground power sources. It employs an auxiliary power unit to supply power for on-ground air conditioning, lighting, and engine starting. This program will demonstrate the correct operation of the APU in normal, abnormal, and emergency situations. The APU is a small turbine engine housed in a fireproof enclosure in the rear fuselage. It may be run unattended due to automatic regulation and automatic shutdown in case of overspeed, low oil pressure, or fire. The fireproof APU enclosure is ventilated for cooling during operation by air drawn through the ventilation duct on the left side of the fuselage. Air for combustion is ducted from an inlet on top of the fuselage. A third duct supplies APU bleed air to the aircraft. Exhaust gas and ventilation air are expelled through a port on the right side of the fuselage. When the APU is not running, the ventilation, intake, and bleed air ports are closed by the ventilation air valve, the air intake door, and the bleed air valve. The air intake door and ventilation valve are opened as a first step in the starting sequence. The APU incorporates an electric starting motor. Normally, power for starting the APU is supplied by the aircraft's battery, although external DC power can be used for this purpose. The starting cycle is completely automatic. The fuel control unit meters the fuel, while the APU control unit governs ignition and starter motor sequence. When the turbine reaches operating speed, the fuel control unit maintains constant RPM at 100% during normal operation. The APU generator does not use a constant speed drive, but otherwise it is identical to the engine-driven generators. It has been certified for in-flight operation and can be used to supply power if one of the engine-driven generators fail. Bleed air is taken from the APU compressor section and supplies power for engine starting and on-ground air conditioning. If APU bleed air is being used, TGT is limited by reducing air offtake. This is accomplished by the load thermostat, which adjusts the bleed air valve position. The overspeed protection unit automatically shuts the APU down should the RPM exceed 110%. A sensing loop in the APU enclosure is connected to the APU fire detection control unit. In case of fire, this unit shuts down the APU and closes the air inlet and ventilation valves. After a 5-second delay, the APU fire extinguisher discharges into the APU enclosure. The main cockpit component of the auxiliary power unit is the APU control panel. It is located on the overhead panel to the right of the electrical power panel. The gauge in the upper corner of the APU panel indicates TGT. A yellow band between 650 and 705 degrees indicates caution. The red line at 705 degrees denotes maximum allowable TGT. Note, however, that during startup, the TGT may indicate as high as 705 degrees for a few seconds. Below the TGT gauge is the APU RPM indicator. The green zone extends from approximately 95 to 105%. The red line, located at 110%, indicates maximum RPM. This is the speed at which the overspeed protection unit will automatically shut down the APU. To the left of the RPM indicator is an AC load meter, which indicates the load on generator 3. The calibration 1.0 corresponds to maximum continuous load. Beneath these gauges are the APU control switches and additional indicators. The main switch controls the ventilation air valve and air intake door. With the switch off, both will be closed. With the switch on, both will open. The opening sequence takes approximately 10 seconds, and the starting sequence cannot be initiated until both are fully open. In the lower right corner of the panel is the combined APU start button and starter motor on light. The light will illuminate when the start button is pressed and will stay lighted as long as the starter motor runs. To the far left of the panel is the generator 3 switch, which works in conjunction with a generator inoperative light. With the APU main switch on and the generator 3 switch in the center position, the inoperative light will be on. With the APU running and the switch in the on position, generator 3 will be operative and the amber light will extinguish. The test position for this switch is for maintenance purposes and has no function for the pilot. The switch to the right of the main switch is used to control the bleed air supply from the APU. When this switch is turned on, APU bleed air is made available for use in air conditioning and engine starting. Beneath the main switch is the Stop Overspeed Test button. This button is connected to the overspeed protection unit and when depressed simulates an overspeed. The button is used to stop the APU. Therefore, each time the APU is shut down, the overspeed protection device is tested. To the left of the overspeed test button is the overspeed warning light. When the overspeed protection unit shuts down the APU, this light illuminates and stays on to indicate that an overspeed has occurred. The APU fire extinguisher test light and test reset switch are located on the center section of the secondary instrument panel. If the battery bus is energized and this light illuminates, it is an indication that there has been a discharge or failure in the APU fire extinguisher bottle. To test the system, press and hold the test switch. After 5 seconds, the test light illuminates if the system is functional. The white APU light, located on the left-hand instrument panel, will illuminate if the APU main switch is on. It is powered from the AC bus. Finally, located on the glare shield panel is the wire-locked APU fire guard warning light. Beneath the guard is the extinguisher switch. If a fire occurs in the APU compartment, the light will illuminate and a bell will sound. Operation of this system will be covered later in the program. Before starting the APU, test the APU fire warning system. Move the test switch to the test position and hold it there until the extinguisher light illuminates. This will take approximately 5 seconds. Silence the fire warning bell. Check APU fire warning light on. Reset the test switch. The first step in starting the APU is turning the main switch on. The generator 3 inoperative light should illuminate. Check that generator 3 and APU air switches are off. Wait 10 seconds for the intake door and ventilation valve to open. Then press the starter button. The light should illuminate, indicating that the starter motor is running. Monitor the TGT and RPM gauges. At about 10% RPM, TGT should begin to rise. By 50% RPM, the starter button light should have extinguished. TGT and RPM should stabilize within a few seconds after RPM reaches the normal operating range. Generator 3 can be switched on immediately. However, it is recommended that you wait a few minutes before switching on bleed air to reduce thermal shock. When APU bleed air is switched on, RPM may drop slightly and TGT will rise. While the APU is running, occasionally check TGT and RPM. Both indicators should be stable. It is recommended that the APU be left running during flights of less than a half-hour's duration. This can substantially reduce maintenance cost for the APU. When shutting down the APU, it is recommended that you wait a few minutes after switching off bleed air to reduce thermal shock. Then switch off generator 3 and press the Stop Overspeed Test button. The RPM indicator will deflect to 110% and the overspeed test light will illuminate. Both RPM and TGT should begin to drop. Turn the APU main switch off, but wait for at least 10 seconds before turning off the battery switch to allow the intake door and ventilation valve to close. If the amber extinguisher test light comes on, it is likely that the extinguisher bottle has discharged. You should not start the APU until the problem has been corrected. If pressing the overspeed test button fails to shut down the APU, you should suspect a malfunctioning overspeed protection circuit. Shut the APU down by using the main switch and report the problem to maintenance. Do not start the APU until the problem has been rectified. Should TGT rise above 650 degrees, reduce the load by switching one of the air conditioning pack main switches to the off reset position. Monitor TGT, and if it still fails to fall below 650 degrees, switch off the other pack. If at any time TGT exceeds 705 degrees, the APU should be shut down immediately using the main switch. If the starter fails to disengage, the amber start light will remain on beyond 50% RPM. Shut down the APU using the main switch. However, if no external air pressure is available and immediate engine starting is necessary, Let the APU run and start the first engine without delay. Then, shut down the APU by using the main switch. Check the Abnormal Procedures section of the flight manual for details of other abnormal indications. The only emergency situation associated with the APU is a fire in the APU enclosure. In that event, the following sequence occurs automatically. The APU fire warning light, fire bell, and external fire horn are activated. The APU shuts down. Ventilation valve and air intake door close. And, after 5 seconds, the fire extinguisher bottle discharges. You should silence the bell, then lift the fire guard and move the extinguisher switch to the left. This manual drill ensures that the bottle discharges, providing a backup for the automatic system. Note that the fire warning system for the APU is self-canceling. In other words, when the fire condition no longer exists, the fire warning light and bell will cease to operate. The extinguisher light will remain illuminated and cannot be reset from the cockpit. Because of its automatic features, the APU adds little to the pilot's workload. However, using some care when operating the unit will pay off in improved reliability and extended service life.
This is the first in a series of 4 programs concerning the F-28's power plants. When specific figures or procedures are quoted in the programs, they apply to the 15H and 15P series engines, which are used in Mark 3000 and 4000 aircraft. Differences between the 15H and P engines and the 15 series engines used on earlier aircraft are detailed elsewhere. The Fokker F-28 is equipped with 2 fuselage-mounted Rolls-Royce RB-183 engines. These engines are of the twin-spool bypass type, and each produces about 10,000 pounds or 4,500 kilograms of thrust. The LP spool consists of a 4-stage compressor driven by a 2-stage turbine. The HP spool consists of a 12-stage compressor driven by a 2-stage turbine. The engine has 10 interconnected combustion chambers. 2 of these are equipped with igniter plugs to initiate combustion during engine starting. A dual ignition system, which can be supplied by either AC or DC, energizes the igniter plugs. A portion of the LP compressor output is used to cool parts of the engine and to pressurize oil seals. Additional air from the HP compressor is also used for internal cooling. 2 taps on the HP compressor section provide air for anti-icing, pressurization, air conditioning, and cross-bleed engine starting. A tap at the 7th stage provides low-pressure bleed air, while a tap at the 12th provides high-pressure bleed air. The selection of high or low pressure is automatic. At high engine speeds, low pressure is used. At low engine speeds, high pressure is used. A gearbox driven by the HP shaft drives the fuel pumps, generator, hydraulic pumps, and other auxiliary units necessary for the operation of the engine and aircraft. The only drives taken from the LP shaft are those for the cockpit LP RPM indicator and an LP shaft governor. The engine starter motor is air-operated and rotates the HP shaft through the HP shaft gearbox. Air for starting is supplied by the aircraft's bleed, which can be pressurized by the APU, a running engine, or an external air supply. The starter valve controls the operation of the starter motor. In a normal start, the valve opens electrically when a cockpit switch is actuated and closes automatically before idling speed is reached. Ignition is also controlled automatically during the starting sequence. The ignition system consists of two ignition units, one AC powered, one DC powered. During a normal start, only the AC unit is used. DC ignition is provided for relights and for times when it is necessary to start an engine with no AC power available. An engine-driven low-pressure fuel pump delivers fuel through two oil coolers, one for the engine, one for the CSD. After flowing through a filter and a flow meter sender, fuel arrives at the engine-driven HP pump. The HP pump, in turn, delivers fuel to the fuel control unit, which supplies the engine with a quantity of fuel which depends on throttle position, engine variables, and ambient conditions. Finally, fuel passes through an HP fuel valve before it is atomized by the spray nozzles. This valve has three positions: shut, open, and start. The start position supplies additional fuel to the spray nozzles to facilitate engine starting. The output of the fuel control unit depends on several inputs, the primary one being throttle position. Secondary inputs include HP RPM, LP RPM, thrust, and TGT. At full throttle, the fuel control unit will restrict HP RPM to the maximum permissible value by trimming fuel flow. However, HP RPM may be limited to less than maximum by the action of the other secondary inputs to the fuel control unit. To prevent LP RPM from exceeding its maximum, fuel flow can be controlled by an LP shaft governor. Controlling the fuel flow to limit LP RPM can result in the maximum HP RPM not being attained at full throttle with low ambient temperatures. Compressor outlet pressure, and therefore the thrust of the engine, will increase as ambient temperature decreases. To prevent compressor pressure from exceeding a maximum, the fuel control unit cuts back on fuel flow at low ambient temperatures. This can result in maximum HP RPM being unattainable at full throttle. The top temperature control system will operate at either of two maximum TGTs, one for takeoff and a lower one for climb and cruise. The modes are cockpit selected. When the reference temperature for the selected mode is reached, fuel flow is automatically trimmed to limit turbine gas temperature. Under this condition, maximum HP RPM will not be attained with the throttle fully open. To summarize, Thrust limiting and LP/RPM limiting have their greatest effects at low altitudes and low ambient temperatures. Top temperature control, on the other hand, has its effects only at high ambient temperatures. HP/RPM limiting comes into play only when none of the other controls is limiting. Each engine includes an LP shaft failure mechanism. If an LP shaft fails, this mechanism will shut down the affected engine by closing the HP fuel valve and will lock the HP valve cockpit control. Oil is distributed from the engine's oil tank to the various parts of the engine by a single pump. The oil passes through a fuel-cooled oil cooler, is delivered to the engine bearings and gearboxes, and then returns to the tank. The constant speed drive oil system is independent of the engine oil system. Cooling of the CSD is effected by passing CSD oil through the fuel-cooled CSD oil cooler. Engine ice protection is provided by hot air tapped from the 12th stage of the HP compressor. This air is ducted via two redundant valves to the inlet guide vanes, the nose fairing, and the nose cowl. An inoperative engine is anti-iced by bleed air from the operating engine, provided the throttle of the live engine is set at less than 95% HP/RPM. At higher throttle settings, priority is given to ensuring that maximum power will be available from the operating engine. This program has been the first in a series of 4 programs on the F-28 power plant. The remaining power plant presentations will cover cockpit controls and indicators and operating procedures.